All right, today we're taking a look at section 2.3, which is other set operations. So we've only really seen two descriptive ways to talk about sets in their relationship to one another. We've talked about complements, so it's sort of like the opposite. If I'm a set, the complement is everything that's not inside of me. And then if we're talked about proper subsets and subsets, we talked about that and how the containment works for subsets. So we're going to move a little bit beyond that to some different types of set operations in this section, 3 of them in particular. The first set operation we're going to talk about is set intersection. The set intersection is the set of all elements common to both sets. And you can think about that word intersection just like the intersection of two streets. It's the same thing, or the intersection of two lines. Intersection means the place where they cross. What do they have in common? So if we talk about the intersection of Kickapoo and MacArthur, it's like the actual crossing spot, not OBU and not the UPS store, not Brahms, right? It's none of those places. It's the part where they actually meet in the middle, where both streets, you're on both streets at the same time, what they have in common. Now, a couple of you in the back had asked me how to write something in set notation, and so I'm actually going to be doing that in this lesson as well, showing you how we notate that with set notation. So if we are doing an intersection looks like an upside down U. You can think of it looking like kind of like the letter N, you know, without the bar on the left, okay? Intersection. And in order to be in the intersection, your X value has to be in A and in B. That's what an intersection is. It's an item that has in both sets. Now we've seen some items in both sets. They were subsets. It happened, okay? But they had these sort of really special properties where one of them was completely inside of the other one, right? That doesn't happen always with intersections. So visually speaking, let me show you what a Venn diagram looks like for this. So draw yourself a rectangle. And what I'd like for you to draw inside the rectangle is 2 overlapping circles. Something like that. It's the universal sets the rectangle. We'll make one circle A and one circle B. Visually speaking, where do you suppose my intersection is? Where they cross. It's this piece right here. That's the intersection. All right, another set operation is called union. A set union is the set of all objects in one set or the other or both. So a union notation, it actually looks like a U. And this is all X such that X is in A or X is in B. And in terms of notation, we don't really need to write or both. If it helps you to remember that, feel free to write it. But the word or means that it could be both. It actually has that sort of meaning automatically. All right, notation aside, we've got a Venn diagram that goes along with this. So we'll draw the same overlapping circle kind of thing that you just drew a minute ago. Oops, there we go. So the union means that it's supposed to be in A or in B or both. So what part of this picture am I going to shade if I'm representing the union? Everything in either one. So I get all of this. I talked about intersection being like the intersection of streets. We use that in our just regular language all the time. Another place that we see, or a place where we see another one of these terms, the word union, is we see the word union used in a marriage ceremony, okay? We even call it a union, right? When you get married, call union. So what a union is much like it is in a marriage ceremony. When you get married, you know, you get my debt and I get your debt. You get my money and I get your money. And if you have kids, they become our kids, right? There's no yours, mine, and ours. That's not really how marriage is supposed to work. It's supposed to be a blending of everything that you have. So that's what we mean by union here as well. We get it all. We get the stuff that A only has, the stuff that B only has, and the stuff that they have in common. Okay? So let's take a look at an example where we have that going on. Oh, there's one more. I'm sorry. I forgot about this guy. Relative difference. A relative difference is the set of all elements in one set that are not in the other. Difference we usually think of as meaning like subtraction. So we're not really subtracting here, but that still is the notation that we use. A minus B. And this is the set of all x such that x is in A and x is not in B. So draw that same picture with my overlapping circles. And if I have A over here and I have B over here, and this is my universal set, what part of the picture would fit that description? Sorry, I was distracted. It sounded like somebody's tapping at my door. One more time. What was that? Close. There you go. So it'll be this part of A, sort of the moon shape, right? The part of A that doesn't cross into B. That's relative difference. All right, and we're going to do an example now with some people. We're going to consider Mary. She's a single mom to one child, Mark. And Joe is a single dad to two children, Jack and Jill. Mary and Joe get married. That's that union I was talking about, right? Together they have two children, Ann and Andy. If M is equal to Mary's kids and J is equal to Joe's kids, find and describe the following. So, M is Mary, J is Joe. What would M intersect J be? It would be Ann and Andy, which are the kids they had together, right? So, and of course, we're talking, biological kids for the sake of this argument. So, the kids they have together. So, like you said, that would be Ann and Andy. What would M union J be? All the kids. It's the family picture part, right? You send out the family picture with your Christmas card kind of thing or whatever. You include them all. Don't care if they live here all the time, they still get included in the family picture. So this would be Mark, Jack, Jill, Ann, and Andy. What would M minus J, or the relative difference of M and J, be? It would be Mary's kids only, right? They're only Mary's kids. So which ones are only Mary's kids from that list? Mark. Just Mark. Just Mark. Right? Relative difference means that we don't include Joe's kids. So in this sense, you could describe it as sort of the kids she started out with, right? What she came into the marriage with, in this case, Mark. All right. There's some really nice things that come with unions and intersections, and they come with some properties. The properties they come with are commutative and associative and distributive properties. Now, you've probably seen these properties in whole number operations and integer operations and things, and we'll talk about these on a regular basis. Every time we enter a new chapter in this book, we talk about these properties as it relates to those types of numbers. So this is the place where we're going to do that. When we're looking at sets, So for all sets A and B, the intersection of A and B is the same whether you write A intersect B or B intersect A. And again, think about the intersection of the streets. If I tell you the intersection of Kickapoo and MacArthur, I tell you the intersection of MacArthur and Kickapoo, it's the same thing, right? There's no difference. How about union? Well, if I do the union of A and B or I do the union of B and A, same thing. No difference. You can go back to the pictures that we talked about, right? It doesn't matter whether I'm starting with A or starting with B. I get the same shaded region when I'm done. Associativity. So this would be actually for all sets A, B, and C, because associativity has to do with grouping arguments. So if I have the intersection of A and B, and then I intersect that with C, that's the same as the intersection of A with B intersect C. It doesn't matter which part I start with. Intersect two of them and then intersect it with the third. Makes no difference which two you start with. And the same is true for union. A union B union C is the same as A union B union C. Okay, so there's one more property specifically related to sets, and then there's one that's a similar description, but not really the same. This one again is for all sets A, B, and C. And this is the distribution of intersection over union, and this looks like the following. If I have A intersect B union C, this is the same as having A intersect B, union A intersect C. So in other words, if I were to take the intersection of a union with a set, it's the same thing as taking the intersection of that sets individually and finding the union afterwards. Works the same way. All right, the last one in this sort of like description of properties is a property really about the number of items, the cardinal number in the set, not a set, the sets themselves. This says the following, and then I'll show you a picture of what it means. The number of items in A union B is the number of items in A plus the number of items in B minus the number of items in A intersect B. And I'd like to justify for this for you with a picture. Okay, so I don't actually have things inside my Venn diagram. I have space. So we're going to use the space to represent whatever's in that space. Circle A. I'm going to shade it in green. If I had things inside of this, right, everything in green would be the number of items in circle A. Agree? Sure, no problem. And if I then wanted to talk about the number of items in circle B, I would shade like this, and that would be the number of items in circle B. But what happened when I shaded both those regions in the middle of the graph? The middle was counted twice. It was counted when I counted the green, and it was counted when I counted the blue, right? So in our formula, if I add the number of items in A to the number of items in B, I need to subtract one time the intersection because I double counted it. Does that make sense? I need to remove my double count. I feel like we've talked about removing double counts like at least 3 times at this point in very different contexts, but I do have to remove that double count. Okay, there is one more set operation that I want to show you, and it's called a Cartesian product. And then we're going to do a couple of examples. The Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. You could almost think of this like if you were working in your closet and all of your first set is your shirts and all of your second set is your pairs of pants, and you were looking for all the outfit combinations that you could choose. Okay? If you want to think more, technically mathematical, you can talk about the XY coordinate plane, right? X's and Y's. X is your first set, and Y is in your second set, and so forth. So let me show you how this looks in terms of just a real quick example. So let's say set A has elements X, Y, and Z, and set B has numbers 1 and 2. Now there's nothing that says that A and B have to actually even be different. They could be the same, and it would be okay in the way this is actually set up. But it's easier to see if I make them different. So if I wanted to find the Cartesian product, it's actually described using that multiplication kind of symbol for X between them, for product. And what this is it's a set of ordered pairs. I'm pairing up X with 1 and X with 2. And then I'm pairing up Y with 1 and Y with 2. And I'm pairing up Z with 1 and Z with 2. And this would be the Cartesian product. It's a collection of ordered pairs. Right? So again, it's like looking in your closet. If you want to know how many outfits do I have? Well, you could actually pair things up and find out how many different pairings you have. And that would actually give you a collection of ordered pairs. You're right, and you're thinking of is the fundamental principle of counting. Yeah, the fundamental principle of counting is at play here for counting how many things you have. So let me actually show you that. So let's notice that the number of items in A, in our case here in this problem, was 3. And the number of items in B was 2. While the number of items in the Cartesian product is actually 2 times 3, or 6. And that always happens. Now, notice the difference. This is actually the Cartesian product. This is the number of items in it. So if you were asked to find the Cartesian product and you told me 6, you didn't find it. You found the cardinal number of it, and that's a different question. But if you were asked to find the cardinal number, then the fundamental principle of counting is the easiest way to do that. Okay, so it is a true statement, if I kind of put that all together, that the number of items in the Cartesian product is equal to the number of items in each individual set multiplied. Okay, so we've been working a bit more today with Venn diagrams, these visual pictures of logic arguments. And we're going to continue along that pattern and talk about how we would compare different operations together. So we're going to use a Venn diagram to shade the following sets. And I am very particular about how you're going to do this. So the steps that I'm showing, the work that I'm showing is exactly what I expect for you to show. And here's why. It works no matter how complicated the Venn diagram gets. So I'm showing it to you some very small cases, very simple cases to start with, not because maybe you couldn't figure them out a different way, but because the whole goal is to use this organized, structured way of doing it so that when they get really complicated, it'll still work. Does that make sense? Do you have a question? Okay, just checking. No, just checking. Okay. So first thing to realize is however many letters are written in this argument is how many circles you're going to have. So I have A and B here, right? So I'm going to have 2 circle Venn diagram, just like I've been drawing. So a circle or a rectangle with two circles inside, they're going to be labeled A and B. And they've got the universal set U on the outside. Okay, so nothing is different than I've drawn so far, but it's about to be. There are 4 different regions that this picture has now split the rectangle into. Do you see 4 distinctly different locations that you could be in? Okay, we're going to number them. Technically, you can number them in whatever order you like. You'll be my better friend if you number them the same way I do because it makes my grading life a little bit easier. All right? If you don't, I'll be okay. But 1, 2, 3, straight across through the middle of the circles, and then put the 4 on the outside. So what we just did is we gave the regions names. The names we gave them is 1 through 4. Could you give them letter names? A, B, C, D? Absolutely. Wouldn't hurt anything at all. So if numbers bother you, give them letter names. Okay? So what I want us to do, though, is I want us to think about these sets, namely the sets A complement and B complement, because that's what our problem asks us about. We'll worry about the union part of it next. So I'm not doing that now. All I'm doing is the complements. So in terms of this picture, which of the numbers are in A complement? 3 and 4. I think I heard it finally. A complement means the things that are not in A. That's 3 and 4. So, what numbers are in B complement? 1 and 4. Is everybody good so far? Okay, you are going to be writing numbers down, and you're going to be writing A complement equals these numbers. This is all exactly what you're going to show me when you do your problems. And then we're going to do the full comparison of them, in this case with a union, because that's what we're asked for. A complement, union, B complement. And if you'll remember, union means yours, mine, and ours. We get everything. So the union of the sets 3, 4, and 1, 4 would be 1, 3, 4. You get everything. Okay? This is the work you show, but you still have not answered the question. We're the ones who put the 1, 2, 3s, and 4s. We're the ones who gave that sort of notation. The question actually asked you to use a Venn diagram to shade, right? So we're going to go back to our picture, and we're going to shade regions 1 and 3 and 4. If you have highlighters you want to use it, that's fine. If you just want to shade with pencils, that's cool too. Whatever. Regions 1, 3, and 4. Check out problem B. How is problem B different than problem A? Okay, there looks like there's maybe something distribution going on. We're going to avoid distributing, but I'll show you how. Something else. It's more basic than that. There's 3 circles. Yeah. Do you see A, B, and C listed? This tells me I need 3 circles. So what will that look like? Well, it starts to look a little bit like the Olympic rings, doesn't it? This is 3 overlapping circles, and I need a rectangle around it. Please don't forget your rectangle. It doesn't make sense without it. Okay, I got to have a universal set in which these things lie. So here's my universal set. Again, you can label the circles in any order you'd like. I always label mine from the top left to the bottom right, so A, B, and then C. And no, they won't get any bigger than 3 circles. So you're always going to be either having a 2-circle Venn diagram or a 3-circle Venn diagram. Okay? However, there are more than 4 regions in this drawing, right? Yeah, count them. How many different regions do you see? 8 is correct. So again, I always number top left to bottom right. So this is 1, 2, 3, through the middle, 4, 5, 6. The bottom is 7, and the outside is 8. If you label them differently, it's okay. But this is how I'm going to grade from, so help me out. Help a girl out, okay? Okay, now you go back to the original question. This particular problem does not have any complements, right? The last problem did, so we considered the complement sets. This one doesn't, so we don't. We will only consider, in this case, the original sets. The set A and B will be considered first. Why would I look at A and B and not at C right away? Because they're in parentheses. Yeah, it's really not because they're left to right or alphabetical. It's because they're in the parentheses. So that's where I'm going to start. So looking at set A, what numbers are inside of set A? 1, 2, 4, and 5. In set B, what numbers do I have in set B? 2, 3, 5, 6. Somebody said 4, but it's not. There's not a 4 in that one, right? Just 2, 3, 5, 6. Okay, good. So inside my parenthesis, I did the two individual pieces, and now I have to combine them with the operation it says. And what operation does it say? Intersection. So this is going to be A intersect B. So looking at my numbers, intersection, remember, means what do they have in common? 5 and, 2. There we go. They have 5 and 2 in common. So the intersection is 2, 5, or 5, 2. So what we've actually found is if the question only asked us to do this, we would be done, right? But we have an extra step out here that says union C. So I need to also consider set C. What numbers are in set C? 4, 5, 6, and 7. And then after I consider that, I'm supposed to combine A intersect B, unioned with C. So what does union mean? All of it. So what numbers are in the union of these two sets? 2, 4, 5, 6, and 7. Am I done? No. What do I still need to do? I need to shade. So I'm going to go back and I'm going to say shade 2 and 5 and 4 and 6 and 7. Shading without the work is not going to get you any credit. Work without the shading is simply incomplete, and you would be, a little bit of points taken off. Okay? All right, we will stop there for today.